In 1998, two teams of astronomers were racing each other to answer what seemed like a fairly straightforward question. How fast is the universe slowing down? Not whether it was slowing down. That was assumed. That was considered settled science. Everyone knew the universe had been expanding since the Big Bang. And everyone knew that gravity, the gravitational pull of all the matter in the universe acting on everything else, had to be putting the brakes on that expansion. The only question was how much. Was there enough matter to eventually stop the expansion entirely and pull everything back together in what physicists call the Big Crunch? Or was there too little matter, and the universe would expand forever but gradually slow down like a ball thrown upward that never quite falls back? Both teams were measuring distant supernovae, exploding stars so bright they can be seen across billions of light years, to get the most precise measurements ever made of the expansion rate of the universe. And in 1998, both teams independently arrived at the same answer. An answer that neither of them expected. An answer that neither of them wanted. An answer that broke physics in a way we still have not fully repaired. The universe is not slowing down. It is speeding up. The expansion of the universe is not decelerating under the pull of gravity. It is accelerating, getting faster, every second, every day, every billion years. Something is pushing the universe apart with a force so overwhelming it defeats the combined gravity of hundreds of billions of galaxies. We call it dark energy. And 27 years after its discovery, we still have absolutely no idea what it is. To understand why the 1998 discovery was so shocking, you need to understand what we thought we knew before it. The story of the universe as understood in the late 20th century went something like this. Approximately 13.8 billion years ago, the universe began in an event we call the Big Bang. In that first extraordinary moment, all the matter and energy that would ever exist erupted into being from a state of almost unimaginable density and temperature. Space itself began to expand, and it has been expanding ever since. In the very early universe, this expansion was extraordinarily rapid, driven by the enormous energies of those first fractions of a second. But as the universe cooled and matter formed and gravity began to assert itself, the expansion was expected to slow. This made perfect intuitive sense. Gravity is attractive. Every piece of matter in the universe pulls on every other piece. The galaxies are pulling on each other. The galaxy clusters are pulling on each other. All of it working together like an invisible cosmic brake, gradually slowing the outward rush of the Big Bang. The debate in cosmology was not whether this slowing was happening. It was about what would happen next. The critical question was density. If the universe contained enough matter, above a certain threshold called the critical density, gravity would eventually win. The expansion would slow, stop, and reverse. Everything would begin falling back together, ending in a final catastrophic collapse, the Big Crunch. If the universe contained less matter than the critical density, gravity would not be strong enough to stop the expansion. The universe would expand forever, but it would do so more and more slowly, coasting gradually toward a cold, dark, infinitely spread out future that physicists called the Big Freeze. Both scenarios were bleak in their own way, but both made sense. Both were physically reasonable. Both were consistent with everything we understood about gravity and matter. The supernova teams in 1998 were trying to measure precisely which of these two futures awaited us. And what they found instead was that neither was correct. The tool they used was remarkable. Certain types of exploding stars, called Type Ia supernovae, always explode with almost exactly the same intrinsic brightness. They are what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. The dimmer it appears, the farther away it must be. This gave astronomers the most precise distance measurements ever achieved across cosmological scales. And by combining those distances with measurements of how fast those distant galaxies were moving away from us, derived from the redshift of their light, they could reconstruct the expansion history of the universe going back billions of years. The expectation was clear. Distant supernovae, older ones further back in time, should show a universe expanding faster than the more recent, closer ones. Because gravity should have been slowing things down over time. Old fast. Recent and slow. Simple. What they found was the opposite. The distant supernovae were dimmer than expected. Not brighter. Dimmer. Which meant they were farther away than they should be. Which meant the universe had expanded more than expected since those explosions happened. Which meant the expansion was not slowing down. It was speeding up. Saul Perlmutter is leading one team. Brian Schmidt and Adam Rees are leading the other. Both teams checked their data, then checked it again, then looked for every possible source of error. Dust between galaxies that might dim the supernovae. Systematic errors in their measurements. Problems with their standard candle assumption. They found nothing wrong. The data was correct. The universe is accelerating. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for this discovery. It is one of the most important and most disturbing discoveries in the history of science. Because it meant something was out there, something with enough energy to overcome the gravity of the entire universe, and we had no idea what it was. We still don't. The name dark energy was coined almost immediately after the discovery. And like dark matter, the name is essentially an admission of ignorance. Dark because we cannot see it. Energy because it has to be something with the right properties to drive the accelerating expansion. But what those properties actually represent, what dark energy actually is at a fundamental physical level, remains one of the deepest and most frustrating unsolved problems in all of physics. We know several things about it from observation. We know it makes up approximately 68% of the total energy content of the universe. Ordinary matter, everything you can see, everything made of atoms, every star, every planet, every person, accounts for just 5%. Dark matter accounts for 27%. Dark energy accounts for 68%. The thing we understand least is the largest component of everything that exists. We also know that dark energy appears to be remarkably uniform. It does not clump together the way matter does. It does not form structures. It fills space smoothly and evenly, everywhere, at the same density, regardless of what else is nearby. And most strangely of all, unlike every other form of energy we know, dark energy does not dilute as the universe expands. Normal matter spreads out as space expands, the same amount of matter filling a larger and larger volume. Dark energy does not do this. As space expands, as new space is created, dark energy appears to come with it. The density of dark energy stays constant even as the universe grows. Which means as the universe expands, the total amount of dark energy increases. More space. More dark energy. More dark energy. Faster expansion. Faster expansion. More space. It is a self-reinforcing cycle that will continue for as long as the universe exists. This single property, this refusal to dilute, is what makes dark energy so unlike anything else we know. And so deeply mysterious. So what could dark energy actually be? Physicists have proposed several candidates. None of them are fully satisfying. All of them have serious problems. The cosmological constant. The oldest and still most popular explanation goes back to Albert Einstein. In 1917, Einstein was working on his general theory of relativity, trying to apply his new equations to the universe as a whole. At the time, the universe was believed to be static, not expanding, not contracting, just sitting there, eternal and unchanging. But when Einstein ran his equations, the mathematics kept insisting that the universe should either be expanding or contracting. It refused to sit still. To force his equations to produce a static universe, Einstein added a term to his equations: constant, a fixed energy density associated with empty space itself. He called it the cosmological constant, represented by the Greek letter lambda. It was essentially a mathematical patch, a fudge factor. Einstein himself later called it the greatest blunder of my career, because in 1929, Edwin Hubble discovered that the universe is expanding. The cosmological constant was unnecessary. Einstein abandoned it. But here is the extraordinary irony. When dark energy was discovered in 1998, when astronomers found that something was driving the accelerating expansion, the cosmological constant came back. Because a cosmological constant, a fixed energy density of empty space, would behave in exactly the right way to produce the accelerating expansion we observe. Constant density regardless of expansion, check. Uniformly distributed through space, check. Acts as a repulsive force on large scales, check. The mathematics fits perfectly. The problem is the physics. Because quantum field theory, our best theory of how particles and fields behave, also predicts that empty space should have an energy density. Quantum fluctuations, the constant appearance and disappearance of virtual particle pairs throughout all of space, should give the vacuum a non-zero energy. This is called vacuum energy. And the theoretical prediction for how large that vacuum energy should be, based on our best understanding of quantum physics, is approximately 10 to the power of 120 times larger than what we actually observe. 10 to the power of 120. That is not a small discrepancy. That is not a rounding error. That is the largest discrepancy between a theoretical prediction and an experimental observation in the entire history of science. By an almost incomprehensible margin. If dark energy is vacuum energy, if the cosmological constant is real, then something is suppressing the vacuum energy by a factor of 10 to the power of 120. And we have absolutely no idea what. This problem, the cosmological constant problem, is considered by many physicists to be the most embarrassing, unsolved problem in all of theoretical physics. The second major candidate is called quintessence. Rather than a fixed constant, a static energy density of empty space, quintessence proposes that dark energy is actually a dynamic field. A field that fills all of space, like the electromagnetic field or the Higgs field, but one that changes slowly over time. The advantage of quintessence is that it potentially avoids the cosmological constant problem. If dark energy is a dynamic field rather than a fixed constant, its current value does not have to be explained by the vacuum energy calculation. It could simply be where the field happens to be right now in its slow evolution. The problem with quintessence is that it requires inventing an entirely new fundamental field that has never been detected, and explaining why it has exactly the properties needed to produce what we observe. It also makes a specific prediction that the strength of dark energy should change slowly over time. Current observations are consistent with either a constant or a very slowly varying field. The measurements are not yet precise enough to definitively distinguish between them, but they will be. Modified gravity. A third possibility, perhaps the most radical, is that dark energy does not exist at all. That instead, just as with dark matter, our understanding of gravity is incomplete. Einstein's general relativity has been tested to extraordinary precision within our solar system and in systems of compact objects like neutron stars and black holes. But it has never been directly tested at cosmological scales, at the scale of the entire observable universe. What if gravity behaves differently on those scales? What if the accelerating expansion is not caused by a mysterious energy but by a breakdown of general relativity at distances and timescales we have never directly probed before? Several modified gravity theories have been proposed. Gravity, scalar tensor theories, extra-dimensional models. Some of them can reproduce the observed acceleration without dark energy. But all of them face the same challenge. They have to match general relativity's extraordinary success at smaller scales while behaving differently at cosmic scales. And none of them have succeeded cleanly enough to displace the cosmological constant as the standard explanation. Here is where the story stops being merely mysterious and starts being genuinely terrifying. Because dark energy does not just tell us something strange about the present universe. It determines what happens to the universe in the far future. And the answer depends critically on exactly what dark energy is. If dark energy is a cosmological constant, the universe will continue to expand at an accelerating rate forever. Galaxies beyond our local group are already moving away from us faster than the speed of light, not because they are traveling through space faster than light, but because the space between us and them is expanding so rapidly that the distance grows faster than light can cross it. This means those galaxies are already beyond our cosmic horizon. Their light will never reach us. They have effectively left our observable universe. And as time passes, as the acceleration continues, more and more galaxies will cross that horizon. The observable universe will shrink, not because space is contracting, but because space is expanding so fast that light from distant galaxies can no longer reach us. In roughly 150 billion years, 10 times the current age of the universe, the only galaxies visible from Earth will be those in our local group. Everything else will have crossed the horizon, vanished from our sky. Astronomers of that distant era, if any exist, will look out at a universe that appears to contain only a handful of galaxies. They will have no way of knowing that billions of other galaxies once existed. No evidence, no signal, no light. All the evidence of the Big Bang, the cosmic microwave background radiation, will have redshifted beyond detection. They will live in a universe that appears static and eternal and contains only their local neighborhood. And they will be wrong about everything, just as we might be wrong about something we cannot yet see. Eventually, on timescales so vast they barely have meaning, the stars will exhaust their fuel and die. Black holes will evaporate through Hawking radiation. The last structures in the universe will dissolve into a thin, cold, featureless gas of elementary particles drifting apart in an ever-expanding void. This is called the heat death of the universe, the maximum entropy state, the end of all complexity, the end of all structure, the end of everything. If dark energy grows stronger over time, there is a more dramatic possibility. Some models of dark energy, particularly a variant called phantom energy, predict that the strength of dark energy does not stay constant. It grows. If dark energy grows stronger over time, the repulsive force driving expansion becomes greater and greater. Eventually, it becomes strong enough to overcome not just the gravity between galaxies, but also the gravity holding galaxies together. Then there's the gravity holding solar systems together. Then the electromagnetic forces holding planets and rocks together. Then the forces holding atoms together. In the final moments, the strong nuclear force holding atomic nuclei together would be overwhelmed. All matter everywhere would be torn apart simultaneously. Every atom in the universe ripped into its constituent particles in an instant. This scenario is called the Big Rip. Current observations suggest it is less likely than the heat death scenario, but it cannot be ruled out. If dark energy weakens or reverses, if dark energy is dynamic, if it changes over time, it could potentially weaken, or even a reverse sign, becoming attractive rather than repulsive. In that case, the expansion would slow, stop, and reverse, ending in the Big Crunch, the scenario everyone assumed before 1998. Current data does not favor this. But we have only been observing dark energy for a cosmic instant. We do not know its long-term behavior. We do not know if it is stable. We do not know if it will change. Just when we thought we had at least settled on a working model, even if we did not understand it, new data arrived that complicated everything. In 2024, the Dark Energy Spectroscopic Instrument, DESI, released its first major results. DESI is a spectrograph mounted on a telescope in Arizona that has been mapping the three-dimensional distribution of galaxies across the observable universe with unprecedented precision. By measuring how galaxies cluster together at different points in cosmic history, using a phenomenon called baryon acoustic oscillations, DESI can reconstruct the expansion history of the universe in extraordinary detail. And what DESI found was deeply unsettling. The data suggests, with growing statistical confidence, that dark energy may not be constant, that it may be changing over time, that the cosmological constant, the simple, elegant, mathematically clean solution that has been the standard model of dark energy for over 20 years, may be wrong. The data is not yet definitive. The statistical significance is not yet at the level required to claim a confirmed discovery. But it is strong enough to make physicists genuinely nervous. Because if dark energy is not constant, if it is dynamic, then the cosmological constant is not the answer. And we are back to asking what dark energy actually is without even the comfort of a mathematically convenient placeholder. The DESI results are ongoing. More data is coming. Within the next few years, we will have a much clearer picture of whether dark energy is truly constant or whether it has been changing throughout cosmic history. The answer will reshape our understanding of the ultimate fate of the universe, and potentially the foundations of physics. Step back from the technical details for a moment and think about what all of this actually means. We live in a universe where 68% of everything that exists is something we cannot see, cannot detect directly, cannot explain theoretically, and cannot even agree on the nature of. A universe where the dominant force shaping the future of everything, every galaxy, every star, every atom, is something we discovered by accident less than 30 years ago. A universe that is not just expanding, but accelerating toward a future where everything we can currently see will eventually disappear beyond an unreachable horizon. A universe that will end, whether in the cold silence of heat death or the violent instantaneity of the Big Rip, in ways that make human timescales feel meaningless. And here is what strikes me most about all of this. The scientists who discovered dark energy in 1998 were not looking for it. They were trying to measure something else entirely. They found the most profound discovery in the history of cosmology by accident, while looking for confirmation of something they already believed. The universe did not care about their expectations. It showed them something they were not prepared for, something that broke their models, something that is still breaking our models 27 years later. And that is not a failure of science. That is science working exactly as it should. Every time we look more carefully, every time we build a more powerful instrument or ask a more precise question, the universe reveals that it is stranger and more complex and more humbling than we imagined. Dark energy is not a problem waiting to be solved so that physics can go back to normal. It is the new normal. It is the universe telling us that our best theories, quantum field theory and general relativity, the two most tested and most successful scientific theories in human history, are fundamentally incomplete. That at the largest scales, at the scale of the cosmos itself, something is happening that neither theory can fully explain. And finding out what that something is will require a revolution in physics at least as profound as the one that produced quantum mechanics and relativity in the early 20th century. So here is where we stand. The universe is 13.8 billion years old. It is expanding, and the expansion is accelerating. Something called dark energy, making up 68% of everything, is driving that acceleration. We do not know what dark energy is. We do not know if it is constant or changing. We do not know if it will grow stronger, weaker, or stay the same. We do not know how it fits into our fundamental theories of physics. We do not know why its observed value is so incomprehensibly different from theoretical predictions. and we do not know what it will ultimately do to the universe we live in. What we do know, what 1998 taught us permanently, is that the universe is under no obligation to behave the way we expect. It has its own agenda, its own timeline, its own ending. And dark energy is the clearest reminder that the universe is not finished surprising us. Not even close. In 1998, we thought we knew the basic shape of cosmic history. We were wrong. In 2024, DESI told us we may have been wrong again. I wonder what the next discovery will be. I wonder what assumption we are making right now, sitting here, confident in our models, that will be overturned by the next generation of telescopes. The James Webb Space Telescope is already showing us galaxies that should not exist given our current models of cosmic evolution. The Vera Rubin Observatory is about to map the universe with a precision we have never achieved before. DESI is still collecting data. The Euclid Space Telescope, launched in 2023, is mapping the geometry of the universe across 10 billion years of cosmic history. All of these instruments are pointed at the same question. What is dark energy? And somewhere in the data from one of these observatories, or perhaps from an instrument not yet built, asking a question not yet formed, the answer is waiting. It has been waiting since before the Earth existed, since before the sun ignited, since before the first stars lit up the darkness of the early universe. Dark energy has been there since nearly the beginning, quietly accelerating everything, slowly emptying the observable universe, patiently working toward whatever ending it has planned for all of this. We just found out it existed 27 years ago. We are just getting started trying to understand it. And that, in a universe 13.8 billion years old, is both the most humbling and the most exciting thought I can imagine. We are early. There is so much still to find. If this is the kind of question that keeps you up at night, you are in the right place. Subscribe, because we are nowhere near done.